and welcome back to my channel. Today in this video, we're here at Johns Hopkins to interview Dr. Massimo Stiavelli. And I'm so excited because he is one of the most knowledgeable astrophysicists in the whole world. So let's get right into the video. Because in this video, we're going to be talking about the James Webb Telescope and space exploration. So now let's actually get right into the video.
After the Big Bang, the universe is made mostly of hydrogen and helium. These are the two lightest elements. The way JWST works, it works best to study planets around red stars, not yellow stars like the Sun. There are 18 segments, hexagonal segments, that are deployed to form a single 6.5 mirror, and they need to be aligned with extreme precision.
Hey guys, we have the exceptional Dr. Massimo Stiavelli, and we are going to be interviewing him right now. So, what inspired you to actually get into astrophysics?
Well, when I was 8 years old, I watched Armstrong set foot on the moon, and that's a very impressive thing for a kid. And so, following that, I decided I wanted to do something having to do with space or astronomy or physics, and I managed to do it.
Okay, so you just got inspired by the fact that Neil Armstrong, the first man to get on the moon.
Yeah.
You just like, I want to work in that. I want to work in that domain.
I was always interested in science, but all of them, reading about geology, biology, all kinds of stuff. But I was a nerd, so I would read about science even as a kid. But the landing on the moon was such a big event that really caught my attention.
All right. And well, when did you actually start? When you were 6? You just started learning about astrophysics when you were 6, or when?
Yeah, I started, of course, with books that were age adequate, and I had the advantage at the time that there were no computers, so no video games, no distractions. So I would spend a lot of time on books and trying to learn as much as possible about the world.
Okay, what helped you to start? Like what helped you to start in your passion?
Well, my parents were not wealthy, but they supported my curiosity. So they encouraged me, and whenever they could, trying to get I think when I was in middle school, buying a telescope and trying to give me encouragement to get into science.
Right, so you're going all about the astronomy, astrophysics domain.
Yes.
Okay. Basically the space guy. Okay. So now let's ask you some questions more specifically on space exploration and the GWST, the James Webb Telescope. So what inspired you to pursue a career in astrophysics? You already said that.
Yeah. Actually, for a while in college, I thought I would go into physics, but then I went back into astronomy. I didn't like very much what theoretical physicists were doing in those days, which is things like supersymmetry and string theory. I didn't find appealing, and I thought that going into astronomy, one could do. It was more human-sized research. Also in experimental particle physics, the groups were starting to be huge. You needed super expensive equipment, and I very naively thought, in astronomy, it's more, smaller teams, cheaper instruments. Yeah, little did I know.
And how did you end up at the Space Telescope Science Institute in Baltimore?
The Hubble Space Telescope, like the James Webb Space Telescope, is an international mission. It has a participation from the European Space Agency. And so I discovered that there were openings but from the European Space Agency to for astronomers to spend time in Baltimore. So I applied and was accepted. I had been in Baltimore a year earlier for a couple of months for a scientific collaboration, and I really liked the atmosphere at the institute, the excitement. They were preparing the Hubble deep field, the original one, and so I decided that's the place I wanted to be.
All right. Oh, but great. Okay, so you were passionate because then, of course, when you were 6, you could see Neil Armstrong go to the moon, and then you were able to then come here, not here, but in the Space Telescope Science Institute in Baltimore, because, well, coincidentally, you were in Baltimore at the time.
Well, no, I arrived now.
Yeah, coincidentally,
yeah.
It was the same place where you came to that place. So for some of our viewers who might not know it by now, what is the main difference between the James Webb Telescope, aka the JWST, and the Hubble telescope?
Yeah.
And what is how important is the gigantic leap between these two?
Yeah. The Hubble Space Telescope is optimized for observations in the visible and ultraviolet, and partly thanks to these observations of the Hubble Space Telescope, like for the Hubble deep field that I mentioned, astronomers realized that there were galaxies more distant than we thought, and in the universe, as objects become more and more distant, their light is shifts toward the red and then the infrared. So if you want to see a galaxy that is very, very far away, you need sensitivity in the infrared, which Hubble, like our eyes, doesn't have. So you need an infrared telescope. So James Webb is larger because it needs to see fainter objects.
6.6 meters?
6.5 meters.
And how tall is the Hubble?
The diameter of the mirror is 2.4 meters.
Oh, okay.
And then it needs to be cool because essentially heat is associated to infrared light. And so if the telescope was warm, it would emit a background that would hamper observations.
All right.
So it needs to be cold, it needs to be large, and it needs to be sensitive to the infrared. And these are the parameters that led to the design that you're seeing.
Okay. So basically the Hubble telescope is a telescope in space, which basically captures and shows us what we would see with our own eyes if we were in space, and we use that just to see how it looks like up there. But then there's something that you can't really see, so that's why you use the James Webb telescope to see infrared. Then, do you use that to trace the Big Bang?
Well, the Big Bang, no, because it's in those very early time, the universe is opaque. So the earliest pictures that we have from soon after the Big Bang come from the cosmic microwave background radiation.
So what do you use again to spot with the infrared? What do you try to spot with that?
Very early galaxies, the first galaxies that formed in the universe.
Oh, so you're trying to see the past.
Yes. Infrared also lets you do other things, by the way,
that's the main use.
Which we are interested in. Like, for instance, there are some molecules that are visible, easier to detect in the infrared. For instance, carbon dioxide, to some extent water. And so if you are looking for
exoplanets,
these molecules on exoplanets, the infrared is good. Another thing that infrared does is that if you have regions in our own galaxy, so cosmic scales pretty close to us, even though it's still, thousands of light years away, these regions can be full of dust, and dust absorbs visible light. So you don't see much because of this distributed dust. The infrared can penetrate through dust, so you can see things that wouldn't be visible by Hubble simply because of the infrared radiation of James, the sensitivity of James Webb. And by the way, Hubble also sees where we don't, because as I mentioned, it sees in the ultraviolet, and our eyes are not good for in the ultraviolet.
So it can see what you see and ultraviolet?
Yes.
Oh, so it can do both?
Yes.
And what can ultraviolet see?
Ultraviolet is a higher energy light, so it's bluer than blue, and so.
So it's like that neon blue.
So it's radiation that is emitted by very hot stars, for instance, or black holes that are accreting material and become.
So you use it to retrace black holes and retrace stars eventually.
For instance, yes, yes, in our galaxy.
So it's basically like a Swiss Army knife. You can use it for many things.
Everything.
Cool. Can you describe the role in the development of the James Webb Telescope, and what has been the most challenging part of that?
I was lucky. I was at the right place at the right time. So more or less, I arrived at the Institute in 1995. And 1995 is also the time when the effort to build the next generation space telescope restarted. There had been some discussions in 1989, 1 year before Hubble was launched. But then when Hubble was launched, we discovered there was a flaw in the mirror, the spherical aberration. The mirror was perfect, but of this slightly wrong shape, which created a problem. And so nobody thought about the next telescope until that was fixed. That was fixed in '94, I think. So people started, in '95 thinking about the next step, because these telescopes take a long time to be developed. And I happened to be here and I was interested. So I started working with the people that were developing these concepts. And I've remained engaged throughout the various science working groups, then started working full-time essentially on the James Webb Space Telescope. So I've been involved in every phase of its development, which is, it's lucky because not many people have that opportunity.
So you're like a veteran of it.
Yeah. And
you're still working in it currently?
I actually stopped at the end of April.
Oh, so perfect. You are a veteran.
Because I went on sabbatical, and that means stepping down from what I was doing.
All right.
So you asked about the challenges.
Yeah, what has been the most biggest challenge of that?
Well, there are two types of challenges. One is related to maintaining the interest of the community and Congress in something that is so expensive, and it was, becoming more expensive as time went on. And the other one is trying to do the best you can in terms of the science that the telescope will do. And both things were, present in our minds. One thing that is not just me, the whole group that was providing science advice to the telescope did, I think, very well, was that we focused on science goals that could not be done by anything else. And so whenever there was a cost increase, there would be some review of the science, and independent committees would be asked, is it still worth doing it? And the answer was always yes, because we had focused on goals that nothing else could do. And so it remained goals that were worthwhile and impossible to do with anything else. So that maintained the telescope interest for many years.
Okay. Wow, very, very nice. So there were many, many crises and many things, but then you always had to keep it going.
Yeah.
So what are some of the key scientific goals you hope the GWST will achieve. And can you share any early discoveries or surprises from the data that is collected so far and from, well, the images? Data is basically like the information that you get.
Yeah, two areas that were high in my mind, in priority in my mind, were the study of distant galaxies and cosmology, because that's more or less the original motivation for the telescope. And the other one, the study of exoplanets, so planets in around stars, other stars. And that is interesting because when we started, there were really not many known exoplanets. So we couldn't plan on that. But the design that we developed turned out to be pretty efficient also in studying exoplanets. And so that has been fortunate. And in terms of galaxies, we really want to understand, the very first steps that led us to the objects we see today. So, for instance, something that a lot of people are working on right now is the chemical history of the universe. When, after the Big Bang, the universe is made mostly of hydrogen and helium. These are the two lightest elements. And so most of the things that we are made of, carbon, oxygen, nitrogen in our atmosphere, and so on, those did not exist just after the Big Bang. Those were made in stars. So this transition from the primordial chemical composition and the universe around us today has been brought about by nuclear fusion reactions in the stars. And how exactly did the first generations of galaxies and how we got to the chemical composition of the universe that we see today? We have theoretical models, but whenever we do measurements, observations with James Webb, we find things that we don't quite understand. So that's a challenge, an interesting challenge to have. It forces us to revise our models. For the exoplanets, one of the things that is a little bit, there are many things that are interesting, but one of the things that I personally find particularly interesting is finding a rocky exoplanet, a rocky world like the Earth or Mars, in the habitable zone with an atmosphere. Yeah. This is a very difficult observation for James Webb, but I hope they will be able to do it.
And do you actually know the chances of finding a rocky planet?
Well, my field is galaxies, but I can give it a try. So if you look at our solar system, we have 4 exoplanets. We have 4 planets that are rocky: Mercury, Venus, the Earth, and Mars. And the Earth is in the habitable zone, and Venus and Mars are close, but not quite. Mercury has no atmosphere to speak of. Venus has a very dense atmosphere. We have just...
Is a dense atmosphere good?
Well, it's too dense. That's why there is a lot of greenhouse effect on Venus, and it's super hot. The Earth has the right type of atmosphere, and Mars has a composition that is, in fact, not too dissimilar from Venus, but much, much lighter, much lower pressure. So if we were looking at the solar system from another star, the Earth would be the best bet. We might detect Venus in some techniques better than others, and Mars would be challenging. Of course, Mercury is hopeless. So this gives you an idea of the type of difficulty. The other difficulty has to do with the star that these planets orbit. The way JWST works, it works best to study planets around red stars, not yellow stars like the sun.
Because yellow stars, it's hotter than red stars.
Yeah, but they are also more massive. And so the Earth orbits the sun once a year. if you have a planet in the habitable zone of a red star, since the red star is less massive and less luminous, the planet is further in. So it will orbit multiple times a year. And the technique we use is called transit. We exploit the fact that the planet passes in front of the star to study it. And so if the planet orbits around the star once a year, it's hard to get a lot of data, because if you want to study 10 of these transits, you have to wait 10 years. While if it's a small star, you have many transits in 1 year, and you can study them all, co-opt in the signal, and have a better shot. However, red stars are not as stable as the sun. And so this could create two problems. First, it makes it harder to do the observations because the star is disturbing the system. And second, there are some people that believe that the flares of the stars might impact both the atmosphere, maybe cause it to be lost, and it might even prevent life from forming. So these stars are not super ideal, but still, it would be nice to. A lot of people are still working to find atmospheres around these stars.
And so the GWST, also known as the James Webb Telescope, features so many technological advancements. Which innovations do you find most exciting, and how do you think they will impact the future of space telescope?
Yeah. I remember a meeting of the science working group where one of the members said, well, for JWST to work, we need two miracles. And one was the mirror, and the other one was the sun shield. The mirror is because the 6.5 mirror is too large to be for any existing rocket. So it's segmented. There are 18 segments, hexagonal segments, that are deployed to form a single 6.5 mirror, and they need to be aligned with extreme precision. And nobody had ever done that in space and to the required precision. So they require a lot of attention, a lot of care, and this worked beautifully, in fact, to the level that the mirror is a factor of 2 better than we wanted it to be. So the images are sharper than we thought they would be. The sun shield is needed to cool down the telescope, and it's about the size of a tennis court, and it's super thin, and it needed to deploy without any issue. And that was very challenging because, of course, these happen, unlike Hubble, that is in low Earth orbit. James Webb is very distant, about 1 million miles away, 1.5 million kilometers. And so there was no easy way to help if it didn't work. So it had to work on its own. So that was also quite a lot of attention.
How important is collaboration in your work? And can you highlight any particular memorable experiences or partnerships from your time on the GWST project?
Well, JWST is an international collaboration. So from the start, we knew in order to do it, we needed international partners. So the European Space Agency, that is a partner also for Hubble, was a partner for James Webb. The Canadian Space Agency was a new partner. And in the early discussions, there was also, we had a member of representing the Japanese Space Agency in our group, but then Japan withdrew. So it remains European, Canadian, and the US. By having such an international group, you get access to the best technologies from all these countries and different perspectives, and so it has been a very, I think, successful collaboration.
And you had fun?
Yeah. You have sometimes extra challenges because There are laws that restrict what you can tell people from other countries, but overall I think it was worth it. It was interesting.
Cool. So how do you see the future of space telescopes and astronomical research?
Well, there are two space telescopes. One is being built now, and another one is being designed or conceived now.
Is it the same?
No, two different ones. Then the one that is being built is called the Roman Space Telescope. It has the sign of Hubble, but it's able to take images of a much larger field of view. So you can think of James Webb as going deeper than Hubble, while this new telescope Roman goes wider. It takes much larger fields in a single shot, and it will be. There are many areas of science that is being developed to study. One of them has to do with dark energy, possibly discovering other exoplanets and so on. The next one is called the Habitable World Observatory, and it's a telescope designed to essentially find an Earth analog, a planet like the Earth around a star like the Sun. So it needs to be larger than the James Webb. It will again.
And it's getting built right now.
No, it's being designed, conceived. This will be very far in the future.
Oh. Okay.
But in time for you, I will be retired probably when it launches, and it could exploit some of the technologies of James Webb. For instance, the deployable optics. Maybe it's something that could be relied upon, but it would be very different. It will need better optical quality than James Webb because it will need sharper images in order to suppress the light of the star.
Okay. But isn't that the Hubble telescope already do, the ultraviolet?
Yeah, but these will be bigger and more sensitive.
And more powerful.
And more powerful. So this will, the nickname we use is Super Hubble.
Apple?
Super Hubble.
Oh, Super Hubble. Okay. So how do you think the discoveries made by the GWST and other space telescopes will impact our understanding of the universe?
Well, of course, understanding about the formation of the chemical elements affects us directly, but there are also questions of cosmology that the James Webb is trying to address. There is one little mystery having to do with the expansion of the universe. If different groups using different methods to estimate the expansion rate of the universe, it's called Hubble constant, find different numbers, and if this difference is real, it could mean that there is something we don't understand in cosmology, in how the universe has evolved. And the James Webb can do observations that will help clarify this issue. So that is a way to contribute to the one of the biggest questions about cosmology. And of course, finding exoplanets with rocky world with an atmosphere, which we may or may not be able to do, would also be very important.
All right. So what advice would you give to young scientists and students who are interested in pursuing a career in astrophysics?
Well, it's hard to give advice. I can tell you, the path that I followed, which was, I knew that this is what I wanted to do. I was lucky, so my parents encouraged me to go to college and so on. I went for my passion. I thought, maybe if I go into engineering, it would be easier to find a job than going into physics. But I decided I had the passion for physics, and that's what I did. And then I continued working on what interested me at every time. And I started as a theorist, in fact, using computers and mathematics to study things.
And did you like
And
it?
then that's what I liked. And then I started working with observers, maybe trying to help them explain what they were observing, and I got interested in data, and then I ended up, being involved in building instrumentation. So I had a very convoluted path, yeah, but always following my interest.
Our last question. What has been the most rewarding aspect of your career so far, and how do you stay motivated and inspired in research?
Well, certainly I was highly confident that the James Webb would work.
Does it work?
But seeing it work was very rewarding, particularly seeing it work better than we thought, better than expected. So that has been very rewarding, and a culmination of more than 20 years of effort dedicated to the mission. I don't know. It's a little bit of a gamble, because if it hadn't worked, I would have been asking myself, what did I do the last 20 years of my career? But it worked. The gamble ended up working out.
And so this interview is great. It was really lovely. And yeah, so welcome to the show, family. So good luck.
Thank you.
Thank you.